So we already looked a little bit about probability trees, and we're going to really get into those a little bit more because we can use trees to solve different types of probability problems. So let's say we have the same situation we had before where we have this bag of marbles, and we've got 5 red, 4 blue, 3 white. 2 balls are drawn, one after the other without replacement. So let's draw the tree. So on the first draw we get 3 options, right? And I wish I'd given myself more room. Maybe I can do it over here and have a little bit more room. So red, whoops. Well, since I put a B there, that's going to be B, blue, red, or white. Oh, I can't believe I did that. I'm giving myself a little bit more room. So after I draw one ball, I'll still have the chance to get the 3 different colors. Blue, just going with my mistake, white, blue, red, white, and blue, red, white. Okay, so since I messed up the order, let's see if we can fix that. So when I first draw, the probability of getting a blue one is 4 out of 12. To get another blue one, it would be 3 out of 11. How many reds are still there? 5 out of 11 total. And there's 3 whites out of 11 total. But let's say we drew a red ball the first time. The probability of that happening is 5 out of 12. But I drew a red, not a blue, so there's still 4 blue out of 11 total. But there's only 4 red out of 11. And there's still 3 white balls. How many white balls? There's 3 out of 12 to begin with. If I draw white on the first go round, there's still 4 blue. There's still 5 red. And now there's only 2 white. Now, what's the probability of drawing blue on the first draw and then white on the second? So on the first draw, blue. Second draw, so we took this route. The second draw white would be 3 out of 11, which would end up being 12 divided by 12, so that's going to be 1 out of 11 actually. Oh. Okay, white on both. So white path, then white path. So 3 out of 12 times 2 out of 11. That's 6 out of whatever, 12 times 11. 6 goes into 12 2 times. That's 1 out of 22. Drawing a blue ball and a white ball. But it didn't say what order. So this is kind of an or. So we could have blue, then white, or white, then blue. So we've got 2 different probabilities there, and we're going to add them together because it's either this happens or this happens. So blue, then white would be 4 out of 12 times 3 out of 11. White, then blue would be 3 out of 12 times 4 out of 11. And I'm actually going to use my calculator for this, and I'll show you a neat little trick. I can do the 4 times 3 over 12 times 11 plus 3 times 4 over 12 times 11, and I get 2 out of 11. What's the probability that the second ball is red? So there's a lot of ways that can happen. If we follow the first route, be 4 out of 12 times 5 out of 11. Or it could be this second route where they're both red. Or it could be white then red. And I would use my calculator. And this time I'm going to be a little lazier and go ahead and multiply those numerators because they're easy. And I'm sure it is easy to do 12 times 11, but I'm having one of those days. You end up with 5 out of 12. So having those diagrams drawn out helps you solve it when you've got more than one thing going on. When you have these events that affect each other. So let's look at this one. Quality control. A security system is manufactured with a fail-safe provision so that it functions properly if any two or more of its main components, A, B, C, are working properly. The probabilities that A, B, and C are working properly goes as follows. What is the probability that the system functions properly? So, we got to go through system A, then system B, then system C. Woo! I'm going to have a lot of drawing to do, so I'm going to have to start off pretty wide. Okay, so for system A, we're going to start with system A. It's either good or not, right? Well, let's say good or not. Yeah. Good or it's not. And good for system A is 0.95. And the opposite is 0.05. Okay. Then it's got to pass through the second system, and that's B. So here it's either good or not. Good or not. For system B, it's a 90%. So 0.90, 0.10. 0.90, 0.10. The last system, system C, is either good or not. For each branch, good or not. It gets a little messy. Good or not. And its chances are 92% or 0.292, 0.08 that it's not. 0.92, 0.08, 0.92, 0.08, 0.92, 0.08. So which of these branches will mean that the system functions properly? So let's look back at the beginning. The system functions properly if any two or more are functioning properly. So if they're all three systems are good, we're good. So I'm going to go ahead and multiply that together. So I got 0.95, whoops, turn it back on, 0.95 times 0.9 times 0.92. This branch gives me 0.7866. Now here, good, good, not. We've got to include that one because at least two are good. 0.0684. Good, not good. 0.95 times 0.1 times 0.92. What about good, no, and a no? That doesn't work. What about if I get a no on the first one, then a good, and then a good? Well, that's okay. So 0.05 times 0.9 times 0.92 is 0.0414. What about a no, a go, and a no? What about a no, and a good? What about a no, no, no? Definitely not. So there's 4 ways this could happen. So since I went ahead and multiplied those together, all I have to do is add them up. and I get 0.9838. So the probability that the system is running properly is 0.9838, or a 98% probability. So there's a formula called Bayes' formula. And in Bayes' formula, we know the result of the second stage of a two-stage experiment and wish to find the probability of the specified result in the first stage. So, in other words, the product of the branch probabilities on the path leading to that result through the first one. And then the sum of all the branch products on the paths leading up to that one will go in the denominator. And that looks very confusing, right? Let's break it down. Okay. So, suppose a test, I don't know where this 1 of 2 comes from, don't worry about that. Suppose a test for diagnosing a certain serious disease is successful in detecting the disease in 95% of the people infected, but that it incorrectly diagnoses 4% of all healthy people as having the serious disease. Suppose also that it incorrectly diagnoses 12% of all people having another minor disease as having the serious disease. It is known that 2% of the population do have the serious disease. 90% of the people are healthy, and 8% have that minor disease. So, find the probability that a person selected at random has the serious disease if the test indicates that she does, that it's a true positive diagnosis. So first off, let's draw our chart. So there's 3 people here. We have the people who have the disease, the people that are healthy, and the people that do have an underlying condition. And they said we already know that 2% of the population do have the disease. We know that 90% are healthy and 8% have an underlying condition. Well, each of these people are going to go in and get this test, and they either get a positive or negative when they take the test. All right. It says that the test to find the disease is successful in detecting the disease in 95% infected. So the positive is 0.95 out of the 0.05 here. It diagnoses 4% of healthy people incorrectly. So even though they're healthy, 4% are coming up with a positive. That's 96% that aren't. And it incorrectly diagnoses 12% in the people with the underlying condition. So 88% get a negative. So it says we're going to take the product of the branch probabilities on the path leading to F through E. So what does that mean? So we're finding the probability that a person at random has the disease and has a positive result. Oops. Given that they got a positive test. So what we're really trying to do is, so the probability that they have the disease and the positive test, given that they got a positive test, the probability of getting a positive test. Pos test. Pos test, yeah, okay, that looks like post-test. Okay, the probability that they have the disease and got a positive. That's this route, right? So 0.02 times 0.95. But what are all the ways that we could have gotten a positive result? Well, that is one of the ways, 0.02 times 0.95. But how else could we have just gotten a positive? Well, these people got a positive. These people got a positive. So we're going to multiply the product of the main branch that we're looking at, 0.02 times 0.95, divided by the probability that we just got a positive test, which would be that probability plus 0.90 times 0.04, whoops, plus 0.08 times 0.12, 0.0646. So I'm going to take 0.019 divided by 0.0646, 0.2941. So if we pick somebody at random and they tested positive, there's only a 29% probability that that person actually has the disease. Interesting. So on the back of here is the summary of all the formulas. If you wanted to kind of have that flagged, put a little sticky note or something, because you can refer back to that a lot.